According to the National Electrical Code, specifically regarding ground fault circuit interrupter protection, all 120-volt, 15 amp and 20 amp receptacles located in bathrooms require GFCI protection. However, there's an exception. Receptacles not located within the bathroom area don't necessarily require this protection. The bathroom area is defined as the space within 6 feet of the edge of a bathtub or shower. If a laundry room, for instance, is located outside of the 6-foot area, then the laundry outlets technically don't need to be GFCI protected. The key here is understanding the defined space. The code is very specific about what constitutes the bathroom area for the purposes of GFCI requirements. It is the area within that 6-foot perimeter of a tub or shower. So, a laundry room adjacent to a bathroom but outside that zone does not fall under the specific requirement. An inspector's claim that a laundry area is part of the bathroom simply because it is adjacent is incorrect. The NEC clearly defines that area as the space within the 6 feet of a bathtub or shower. The intent of the GFCI protection is to safeguard against electrical shock in areas where water is likely to be present. This is why bathrooms, kitchens near sinks, outdoor locations, and other damp or wet areas necessitate GFCI protection. GFCIs work by monitoring the current flowing in a circuit. If there is an imbalance, meaning some current is leaking to ground, the GFCI will trip and quickly cut off power to the circuit. This prevents potentially fatal electrical shocks. Now let's delve a little deeper into GFCI technology and its application. Firstly, a standard circuit breaker is designed to protect against overloads and short circuits. It monitors the amount of current flowing through the circuit and trips when that current exceeds a certain level, preventing damage to the wiring and appliances. Secondly, a GFCI, on the other hand, is specifically designed to protect people from electrical shock. It monitors the difference in current between the hot and neutral wires in a circuit. In a properly functioning circuit, the current flowing through the hot wire should be equal to the current flowing back through the neutral wire. If there is a difference, it indicates that current is leaking somewhere, possibly through a person. Thirdly, a GFCI is much more sensitive than a standard circuit breaker. It can detect current leaks as small as 5 mA and trip the circuit in a fraction of a second. This is fast enough to prevent serious injury or death. Fourthly, GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. The NEC specifies the exact locations where GFCI protection is required. Fifthly, there are two main types of GFCIs: receptacles and circuit breakers. A GFCI receptacle is installed in place of a standard electrical outlet and provides GFCI protection only to the outlet. A GFCI circuit breaker is installed in the electrical panel and provides GFCI protection to the entire circuit. Sixthly, when determining whether or not GFCI protection is required, it's important to consider the specific requirements of the NEC. The code is updated every 3 years, so it's important to stay up to date on the latest changes. Seventhly, it's also important to consult with a qualified electrician if you have any questions about GFCI protection. They can help you determine whether or not GFCI protection is required in your specific situation and ensure that the installation is done correctly. Eighthly, remember that GFCI protection is not a substitute for proper grounding. Grounding provides a path for fault current to flow back to the electrical panel, which helps to trip the circuit breaker in the event of a fault. Ninthly, GFCIs should be tested regularly to ensure that they are functioning properly. Most GFCI receptacles have a test button that you can push to simulate a ground fault. If the GFCI trips when you push the test button, it's working properly. Tenthly, if a GFCI trips frequently, it could be a sign of a problem with the circuit. You should have the circuit inspected by a qualified electrician to determine the cause of the problem. Now consider the electrical code more broadly. The National Electrical Code is a comprehensive set of guidelines and standards designed to ensure the safe installation and maintenance of electrical systems. It covers everything from wiring methods and overcurrent protection to grounding and equipment installation. The NEC is not law, but it is widely adopted by states and municipalities as the basis for their electrical codes. This means that electrical installations must comply with the NEC in order to be considered safe and legal. The NEC is updated every 3 years by the National Fire Protection Association, a non-profit organization that develops and publishes codes and standards. The update process involves input from a wide range of stakeholders, including electricians, engineers, manufacturers, and inspectors. The NEC is organized into chapters, articles, and sections. Each chapter covers a specific topic, such as wiring methods or grounding. Each article provides more detailed requirements for a particular aspect of that topic. Each section provides specific instructions for how to comply with those requirements. For example, Chapter 3 covers wiring methods and materials. Article 300 covers general requirements for wiring methods. Section 300.11 covers securing and supporting wiring. The NEC also includes a number of tables and examples to help electricians and inspectors understand and apply the code. These tables provide information such as wire sizes, conduit fill capacities, and ampacity ratings. The examples illustrate how to apply the code in specific situations. One of the most important aspects of the NEC is its focus on safety. The code is designed to protect people and property from electrical hazards such as shock, fire, and explosion. The NEC achieves this goal by specifying requirements for grounding, overcurrent protection, and wiring methods. Grounding is the process of connecting electrical equipment to the earth. This provides a path for fault current to flow back to the electrical panel, which helps to trip the circuit breaker in the event of a fault. Overcurrent protection is the use of circuit breakers and fuses to protect electrical circuits from overloads and short circuits. Wiring methods refer to the way in which electrical wires are installed and supported. The NEC specifies requirements for the types of wiring methods that can be used in different locations and for the way in which wires must be secured and supported. In addition to safety, the NEC also addresses issues such as energy efficiency and accessibility. The code includes requirements for energy-efficient lighting, appliances, and HVAC systems. It also includes requirements for making electrical systems accessible to people with disabilities. Complying with the NEC can be challenging, but it is essential for ensuring the safety and reliability of electrical systems. Electricians and inspectors must have a thorough understanding of the code in order to properly install and maintain electrical systems. There are a number of resources available to help electricians and inspectors learn about the NEC. The National Fire Protection Association offers training courses, publications, and online resources. Many states and municipalities also offer training courses and resources. Furthermore, understanding the concept of grounding is crucial to electrical safety. Grounding is the process of creating a low-resistance path for electrical current to flow back to the source in the event of a fault. This helps to trip the circuit breaker or fuse and prevent electrical shock. There are two main types of grounding: system equipment grounding and system grounding. Equipment grounding connects the non-current carrying metal parts of electrical equipment to the grounding electrode system. This includes things like metal enclosures, conduit, and motor frames. System grounding connects the neutral point of the electrical system to the grounding electrode system. This helps to stabilize the voltage and provide a path for fault current to flow back to the source. The grounding electrode system is a network of interconnected grounding electrodes that are buried in the earth. The most common types of grounding electrodes are ground rods, ground plates, and metal water pipes. The grounding electrode system must be properly sized and installed in order to provide effective grounding. The size of the grounding electrode system depends on the size of the electrical system and the type of grounding electrodes used. The installation of the grounding electrode system must comply with the requirements of the NEC. Improper grounding can create a serious electrical hazard. If equipment is not properly grounded, fault current can flow through a person's body, causing electrical shock. If the grounding electrode system is not properly sized or installed, it may not be able to handle the fault current, which can lead to equipment damage or fire. It is important to have a qualified electrician install and inspect the grounding system to ensure that it is properly grounded. Grounding is an essential part of electrical safety. By providing a low resistance path for fault current to flow back to the source, grounding helps to prevent electrical shock and protect equipment from damage. Proper grounding is essential for all electrical systems, regardless of size or complexity. In addition to grounding, overcurrent protection is another important aspect of electrical safety. Overcurrent protection is the use of circuit breakers and fuses to protect electrical circuits from overloads and short circuits. An overload occurs when too much current is flowing through a circuit. This can happen when too many appliances are plugged into the same circuit or when an appliance malfunctions. A short circuit occurs when a hot wire comes into contact with a neutral wire or a ground wire. This creates a very low resistance path for current to flow, which can cause a large amount of current to flow very quickly. Overcurrent protection devices are designed to trip or blow when the current exceeds a certain level. This interrupts the flow of current and prevents damage to the wiring and equipment. Circuit breakers are reusable overcurrent protection devices. They consist of a switch that automatically trips when the current exceeds a certain level. Circuit breakers can be reset after they trip. Fuses are one-time overcurrent protection devices. They consist of a thin wire that melts and breaks the circuit when the current exceeds a certain level. Fuses must be replaced after they blow. The size of the overcurrent protection device must be properly sized for the circuit that it is protecting. The size of the circuit is determined by the size of the wires and the amperage rating of the appliances that will be connected to the circuit. If the overcurrent protection device is too small, it will trip or blow frequently. If the overcurrent protection device is too large, it may not trip or blow in time to prevent damage to the wiring and equipment. It is important to have a qualified electrician install and inspect the overcurrent protection system to ensure that it is properly sized and installed. Overcurrent protection is an essential part of electrical safety. By interrupting the flow of current when there is an overload or short circuit, overcurrent protection helps to prevent damage to the wiring and equipment and protect people from electrical shock. Finally, wiring methods are also key to electrical safety. Wiring methods refer to the way in which electrical wires are installed and supported. The NEC specifies requirements for the types of wiring methods that can be used in different locations and for the way in which wires must be secured and supported. Some common wiring methods include non-metallic sheath cable, also known as Romex, metallic conduit, and cable trays. Non-metallic sheath cable is a type of electrical cable that consists of two or more insulated wires enclosed in a non-metallic sheath. Non-metallic sheath cable is commonly used in residential wiring. Metallic conduit is a type of electrical conduit that is made of metal. Metallic conduit is used to protect electrical wires from damage and to provide a path for grounding. Cable trays are a type of support system for electrical cables. Cable trays are commonly used in commercial and industrial buildings. The NEC specifies requirements for the type of wiring methods that can be used in different locations. For example, non-metallic sheath cable is not allowed to be used in wet or damp locations. Metallic conduit must be used in these locations. The NEC also specifies requirements for the way in which wires must be secured and supported. Wires must be secured to walls, ceilings, and other structural members. Wires must be supported at intervals that are specified by the NEC. Improper wiring methods can create a serious electrical hazard. If wires are not properly secured and supported, they can become damaged, which can lead to electrical shock or fire. It is important to have a qualified electrician install and inspect the wiring system to ensure that it is properly installed and supported. Wiring methods are an essential part of electrical safety. By properly installing and supporting electrical wires, wiring methods help to prevent damage to the wires and protect people from electrical shock. Therefore, to summarize, always refer to the latest edition of the National Electrical Code and consult with a qualified electrician for specific applications and interpretations.